So welcome everyone to the Bear Beyond the Basics webinar series. Today, the webinar will be featuring Bacterial Decline of Creeping Bentgrass from Dr. Richard Lattin, who's a professor of plant pathology at Purdue University. And these are just some webinar instructions that we have, some housekeeping notes for those of you who are participating that you could go ahead and take a look at. We also just wanted to remind everyone of the remaining calendar of events for the webinars. We will have another one on September 18th talking about snow mold and winter damage prevention. And the sixth one, the final in the series, on November 13th, talking about new technologies for reducing water requirements and promoting plant health. And additionally, this is just a reminder that those of you listening will receive CEU and Bear Accolade points. And at the end of the presentation, we'll be sure to provide you with that 9-digit code. So again, Dr. Richard Lattin will be taking us through the webinar today. And Dr. Lattin is a professor of plant pathology at Purdue University, where he's been a member of the faculty there since 1981. He earned his BS degree from Waynesburg College and his MS and PhD degrees in plant pathology from Penn State University. His appointment at Purdue involves research, teaching, and extension in the area of turf disease management, and his research activities focus on factors that influence fungicide performance, and he also authored the textbook, A Practical Guide to Turf Grass Fungicides, which was published in 2011. So with that, I'll turn it over to Dr. Lattin. Thank you.
Okay, thank you very much. Thank you for the introduction, and thank you for the opportunity to share my thoughts about this bacterial decline of creeping bentgrass. You see on this first slide, I have a quote here, "Not much is known about the association of bacteria with turf." And I always preface my comments about this particular disease or problem with that statement simply because we really don't know as much about the bacteria as we do with all of the fungal diseases of turf. So right now we're really just scrambling to find a solution to this bacterial problem that has been the major concern, or certainly a contemporary concern, over the past 2 years, really scrambling for a solution. And what we've produced happens to be lots of anecdotal information, which would be, some observations and perhaps some empirical data that really hasn't passed through the filter of scientific scrutiny. Few plausible explanations are out there, and to tell you the truth, there are no real solutions. So that's really the starting point that we're at right now. I think everything will change, or some things will change through 2012, but right now we just don't know a whole lot. You'll notice that I call it bacterial decline. Now, as I explained a little bit later, the word wilt is already taken with another disease, and to tell you the truth, from my perspective, wilt isn't always part of the syndrome of this problem. Decline suggests this gradual worsening of a condition that might occur over weeks or maybe a month or so. And so I like the word decline, and the decline also implies that there's some other things going on there, that maybe some predisposing factors to the poor health of the turf. So I use the term decline, and that might change, but this is certainly different from all of the other diseases that we're familiar with. All right, so today, or this afternoon, I have a few objectives here. We'd like to review the history and what we currently know about this particular problem. We'll discuss the nature of bacterial disease, and I have disease in quotes there because I'm not sure how aggressive this particular pathogen is, and so maybe the word disease can be interpreted differently here. As I mentioned before, we don't know a lot about this particular pathogen, and everything we know about bacterial diseases has been gleaned from all of the other research and information and knowledge that's been generated about bacterial diseases of crops. And I've worked with some of those, and I'm very familiar with the nature of bacterial diseases, but no one is quite familiar with the nature of this particular disease on turf, but we're learning all the time. I'd like to address the possible chemical treatments that are out there, some of the things that you've probably been exposed to, and provide an outlook for 2012. So with that, let's take a look at this here. Let's start with some facts. Just a few facts about this bacterial problem. Now, the new disease on creeping bentgrass caused by Acidovorax, which is a genus of bacteria, is different from the bacterial wilt of annual bluegrass caused by Xanthomonas. That's one of the reasons why I don't call this particular problem a bacterial wilt. One, wilt isn't always part of the syndrome, and two, this particular name has already been taken. The difference between Acidovorax and Xanthomonas is as distant as Sclerotinia and Rhizoctonia in the fungal world, and we would never call those two diseases the same name. So I think there's some precedent for not calling two different diseases the same name. And that it might be a semantic issue, but I think in order to keep the communication going, we ought to settle on just one. Acidovorax disease occurs on creeping bentgrass putting greens. This is a putting green disease. There have been kinds of symptoms on fairways and collars, but in terms of isolating and identifying this Acidovorax, it's only come off of putting greens, creeping bentgrass putting greens. Third, only a few turf pathology labs are prepared to readily identify the nature of bacterial pathogens in turf. And I have them listed there: North Carolina State University, Clemson University, University of Rhode Island, Purdue University, and perhaps Michigan State. If I left any of them off, I apologize, but those are the ones I'm quite familiar with right now. And I just mentioned this because there's been a lot of talk and a lot of hype about this. Nobody can really eyeball this disease. So if you have had if someone came and identified this problem on your creeping bentgrass putting green and said, well, you have the Acidovorax disease, it had to come through one of these labs. And if it didn't come through one of these labs, then I would say you probably did not have the Acidovorax disease, or that, at the very least, that identification is not accurate. And if you are acting on that type of information with remedial treatments of any kind, you're acting upon information that's probably inaccurate, and you're not making informed decisions. So with all the hype around, I think it would be wise, if you have had that identification, to know who exactly made the diagnosis and identified that bacterium. Now, this next one is important. No one to date has been able to isolate the pathogen and inoculate creeping bentgrass and replicate symptoms in the field. Okay, now that is extremely important, because all of the information that we know about all of the turf pathogens that we're familiar with, all of the fungal pathogens, have been generated. That information has been generated because we've been able to get a pure culture of the isolate of the pathogen, inoculate the bentgrass, and replicate the symptoms in the field. Okay, show exactly on your putting green, or similar putting green, that we can recreate those symptoms. And for some reason, with this particular disease, conclusions are being drawn without having done all three steps. And I think that's a little bit troublesome, and I think because of that, any of the conclusions that have been drawn based on this so far are at least a little bit speculative or tenuous, to say the least. So, just a few facts here that might put some of this in perspective. Now, I want to discuss the nature of bacterial diseases, but before I do that, I want to provide some contrast with something that you're already familiar with, which would be these fungal diseases. I'm going to grab this little pointer here, Okay, and I have this little pointer. Now, I have a composite slide. Look, here's an image, a microscope image. Okay, I have a couple dozen fungal spores, and some of you probably can identify those spores. And if you're thinking that those are the spores of the gray leaf spot pathogen, you're correct. So we can identify these. They're very characteristic shape. And I have a sketch here of a cross-section of a leaf with a little spore on top of that leaf. And I've identified there the different parts of that cross-section in that schematic. Now, when that spore germinates, you have a little germ tube, and it starts to produce some enzymes which begin to dissolve this cuticle, this little grayish layer up on top here. It will dissolve that, and the mycelium will penetrate into the mesophyll, these green cells in here, and then it will begin to parasitize plant cells, gaining nutrition for itself, enabling the mycelium to grow further. We can recognize this. And then beyond that, this infection produces a recognizable symptom, a leaf spot, and signs such as the gray spores that are produced within those particular lesions. And we have here the damage that we observe in the field. Okay, terrible fairway damage caused perennial ryegrass caused by gray leaf spot. And one more thing, and that is we've been able to take all of that and understand that and recognize that and then bring it to our research centers and inoculate the turf and recreate those symptoms. Of all the 35 or 36 turf diseases that we're familiar with that are fungal diseases, we've been able to do this. But we haven't been able to do this with this Acidovorax. Not yet. Now, this summer may be different, and we'll be talking about something else in the fall. But to date, and here we are, mid-June 2012, we have not been able to do this. And I just want to reinforce the fact that without taking this next step, the conclusions that we draw might be just speculative. So, a couple of things here. One, this fungus, here we have this spore, actively penetrates plant tissues. Bacteria can't do that. Bacteria can only enter the plant through natural openings or wounds. And we'll discuss that as the seminar proceeds. Another neat little thing here that might be inferred from this image here is in this image, we have a couple dozen spores of the gray leaf spot pathogen. And all of this granular, kind of grainy material in the background here, that's all bacterial contaminants. So among these 24 or so spores are millions and millions of bacteria. And that will give you an idea of what we're dealing with when we look under the microscope at bacteria versus these fungal spores that we're familiar with. Definitely a different beast here. Okay, how about some of the symptoms here? Well, we have this type of damage here in this particular slide, in this image. You know, sort of a general decline. The damage, certainly some dead turf. In this particular image, you don't see any particular circles or things like that that you normally would see with many of the fungal diseases. But there's certainly damage to that turf, and the vigor of the turf is going the wrong way. The next thing I'm trying to show here is this etiolation. That's what this elongated kind of leaf without much color in it. And this is one of the things that we often associate with the Acidovorax. Over here we have water soaking. See this brown kind of or olive green sort of area in here on this stem and then in this leaf right here, right at the base. That's what we call water soaking. Very typical that you would get with bacterial pathogens. Then of course you all recognize this wilt, this kind of graying and wilting of the plants. And then this other thing here, this is a microscope slide of a leaf that's been cut, and all of this blue stuff right through here, this is all bacteria. This is the so-called bacterial streaming that we've heard about with bacterial wilt and this bacterial decline, this acidovorax. Now, I'll just make a point here, is that there's definitely damaged turf associated with this, and many times we see this, always we see this bacterial streaming, but we don't always see the etiolation, we don't always see the water soaking, and we don't always have wilted plants. So it's hard to pin this thing down. Now, let's just review some of the historical record of bacterial diseases on turf. Now, I have in these blue boxes up here 4 columns: the disease and the pathogen, the turf host, the conditions associated with the outbreak, and the reference in the scientific literature. And I have 7 rows here. This one is a special row, the first one, and then we have 3 here, and then the next 3. So let's go over the first one. This goes all the way back to 1981, when the Michigan State folks noticed that these outbreaks of damage occurred when we had precipitation and cool nights in the spring and fall on Toronto creeping bentgrass. And that was a special case, that C15 wilt was made about that, and they used an electron microscope to actually observe bacteria clogging up the vascular system of those plants. But at that time, the bacteria were never quite identified. True, there were bacteria there, but they were not identified at that time. So even though it's creeping bentgrass, it was the vegetative strains of creeping bent at that time were involved. That's sort of a separate case, and it's hard to associate that with anything that is happening today. So I just wanted to point that out, that 1981 report was the initial report of some bacteria associated with turf. Now, the next 3, we have the turf host is annual bluegrass, here, here, and here. In each case, called it bacterial wilt, and it was some sort of xanthomonas. And the taxonomists change the names fairly frequently. The current name is Xanthomonas translucens. Dr. Mitkowski in Rhode Island published on that in 2005. There's a popular article by Dr. Dernoden and others in 2003. And of course, the Michigan State Lab actually had identified a xanthomonas in the annual bluegrass back in the mid-1980s. This seems to be a disease of maybe spring or late spring or something like that. Wet conditions are part of it here, and definitely associated with annual bluegrass. Now, let's jump down to the last 3 where we have creeping bentgrass. And here's the first time in the turf literature we see the term acidovorax. It was actually identified by the Japanese. And here it is. Here's a citation here in 2009. They reported on this bacterial brown stripe of creeping bentgrass and identified it as Acidovorax aveni. So, really, if we were to follow the normal conventions, I think the name of this disease might actually be changed to bacterial brown stripe, because it was, in fact, the first time that it was the Acidovorax aveni was associated with the bentgrass. Be that as it may, in 2010, we had the Michigan State folks isolating and identifying this Acidovorax on creeping bentgrass from samples that they got from North Carolina. Hot, droughty conditions. It was a terrible summer for growing grass in 2010, but they did identify as Acidovorax aveni. And then, of course, 2011 and later on in 2010, Acidovorax, summer stress conditions, lots of observations. So that's where we are here. And this is one of the reasons why I don't like to call this particular pathogen or this disease a bacterial wilt. This name is taken. It's a disease of annual bluegrass. We're talking about something caused or associated with Acidovorax, and it might not quite be appropriate to call it the same thing. Okay, next slide here. Now, I think that in order to understand the disease, maybe we ought to be curious enough to ask a few questions. And the first question that would come to mind was, how did this Acidovorax come to reside on my putting green? So there are several possibilities. In the first two, they would be introduced, or first three really, introduced into the putting green, in that it wasn't there before and it was somehow introduced. Was it introduced as fallout from thunderstorms from another part of the country, or mechanical introductions with equipment or golfer's shoes, or perhaps infested seed? Now, we don't discuss this too much with turf diseases and fungi, but in the vegetable and plant ornamental world, seed is commonly associated. Bacteria are commonly associated with seed. In fact, there's actually an Acidivorax aveni bacterium that's actually associated and spread with watermelon seed in watermelon. So that it's well documented. Now, be that as it may, there's no evidence, direct or indirect, to show that this particular pathogen or bacterium was associated with creeping bentgrass disease with seed. There's no evidence to that end. And so, but it's just interesting to know that there are several ways in which pathogens can be introduced onto the golf course or into the grass. Now, the last selection here is D. And that means, was it always there? Okay, rather than it being introduced, it was always part of that microbial community in the rhizosphere. Okay? So those are the four possibilities. And I asked this in my seminars over the winter to superintendents groups, and I compiled the results. And here we have the introduction with thunderstorms, introduction with golfer's shoes or equipment, introduction with seed, or it was always there. And as the superintendents think about this, of course, they figured it out as well as any of us. Most likely it was already there, part of the microbial community in the turf soil. Okay, think about that, all right? The turf environment is very, very complex. There are perhaps 100 million bacteria per gram of soil. That's about the size of a raisin. 100 million bacteria. And within that 100 million, maybe 10,000 different species. We don't know the functionality, inner functionality of some of these. So it would really be unreasonable to assume or suppose that this bacterium wasn't already in the root zone or in the thatch of your putting green. Okay, that would be, assuming that it wasn't there already, would be unreasonable because of the complexity of the turf environment. So, if it's not something new, then why have I not observed it before? Okay, this is a relatively new thing. Okay, so here's the next question that we should be curious about. So there are different possibilities, and again, I posed this to the superintendents groups that I do my seminars with and compiled the results. And they all had some good opinions. We had some good discussion about this. One could be other problems seem to mask the presence of Acidivorax. Okay, you know that when you have stressful conditions, that there are a lot of things that can go wrong on turf, because the turf is weak and it's just predisposed to a lot of different things, and there's a lot of kinds of damage there. And perhaps over the years, Acidivorax was always there, but we just overlooked it because some other things were much more obvious. Another possibility that there are periodic changes in management practices expose the turf to greater risk of bacterial infection. Now, what changes could they be? Well, think about how putting greens are managed now versus, in the mid-1980s or even 1990. We're doing a lot of things different. And the more current species or cultivars of creeping bentgrass, these upright bents, intensively managed bents, require some more aggressive grooming and cultivation in order to maintain these nice, firm, smooth playing surfaces that have little or just the right amount of thatch. So management practices have definitely changed over the past 20, 25 years or so. And then another factor would be the weather during the last 2 summers was unusual. Okay, and I think that's definitely the case too. So it's probably a combination of all these three that created some perfect storm in which this normally benign Acidivorax became rogue and started to cause damage on our turf. Next slide. Okay, now, there's an explanation here, and I just kind of want to take my time because it's a little bit complicated and different than what we normally see with fungi. Or to tell you the truth, it's different even in the cases where we have aggressive bacterial pathogens with crops. Now, let's start with these 2 sketches and my statement here that in most cases, bacteria and turf plants live in relative harmony, even when bacteria find their way into plant tissues through natural openings, okay? There's an equilibrium that has been established between plants and bacteria. Now, in this sketch here, you see these little tiny pink dots here and then here again and here. These are representing bacteria. I already mentioned that these bacteria cannot directly penetrate into plant tissues. They must enter through wounds or through natural openings, which would be the stomates, you know, these little gas exchange pores here, or hydathodes, which are pores on the edges of leaves. So we have this stomate here, it's open, and sometimes bacteria find their way in this substomatal cavity. And there's some kind of innate immune system, I think I have that here, okay, in plants that keeps these bacteria in check. Now, especially when you don't have terribly aggressive bacteria. And what happens is that the plant actually senses that there's some foreign object in this cavity down here, and it dispatches sort of protective compounds or defensive compounds to corral those bacteria and keep them in check and keep them from populating, okay, from the populations from exploding. It's really the populations exploding that causes all the damage. So if the defense compounds can keep these populations low, we won't see any damage. Okay, so healthy plants produce these defense compounds and keep these bacteria in check, and they remain benign even though they might be in the immediate turf environment. Here's another thing, that in some cases, immune systems have been identified that when the plant recognizes bacteria on their surfaces, the stomates, the guard cells close in the stomate, and they prevent these bacteria from entering this substomatal cavity. Okay, so we have a couple of things going on here that are part of this plant's innate immune system. Now, the innate immune system, I doubt, is effective against our fungal diseases and probably not very effective against, in healthy plants, against really aggressive bacterial diseases like they have in many of our crop plants. But here's a different case where if we have something predisposed, a predisposing condition, this normally benign bacterium may not be put in check by the immune system. A couple more sketches here. Okay, just one right here. Here's the deal. In stress plants, the immune system is weakened. Okay, and the bacteria perhaps that have fallen down here sense this. The weakened cells begin to leak. Okay, their membranes fail, they begin to leak. These components that fall out into the intercellular spaces are utilized as nourishment by bacteria. Bacteria multiply, continue to multiply, add even more stress, and all of a sudden these cells begin to collapse at a greater rate, and the populations of bacteria explode. So, in my opinion, it is likely that a combination of stresses push the balance, this normal equilibrium between bacteria and bentgrass, beyond the tipping point. Okay, so why have I not seen it before? The conditions lined up to the point where this normal equilibrium was upset and the bacteria populations take advantage of it. So now, many of you are going to say to me, well, the diagnostic lab told me that they saw bacterial streaming, and doesn't that indicate an aggressive pathogen? And I say to you, it could, but also doesn't necessarily have to mean that we're dealing with an aggressive pathogen. And a couple more sketches might bear that out. Here we have the bacterial population, these small pink dots, rapidly increasing in this cavity. You have cells breaking down here, okay? And when the cells break down, they leak. The components are used as nourishment by the bacteria. So over here, I have an ever-increasing pathogen population that is increasing rapidly, and it just follows the path of least resistance. In some cases, it pushes back out the stomates, and sometimes in the microscope, we can actually see little globules of bacteria coming out the stomates. In other cases, it's pushing through to the plumbing of the plant, and in this case, I show the pressure building up from this huge population of bacteria coming out this end here, this cut end. And that's what I'm trying to show in this slide right here. Here's the leaf. It is cut, and this is dark field microscopy. See all this blue stuff here? These are the bacteria just flowing out of that cut tip. All right. Now, in this particular scenario, the plant was already weakened. The bacterium or the bacterial population took advantage of the weakened cells, used the cell components as nourishment, which increased the population even more, followed the path of least resistance, and started to flow out the xylem. And that's different than if the bacteria itself attacked a healthy plant and itself broke down cells, started to parasitize it, and then started pushing, this chain of events pushing the bacteria out the xylem. So here we have a normally benign bacterium taking advantage of weakened and stressed plants, rather than an aggressive bacterium actively parasitizing a healthy plant. Okay, we talked a little bit about bacteria entering through natural openings, and they also can enter plants through wounds. And of course, in our turf environment, what better wound than the daily mowing that we have? Do you know that inoculation of bacteria into plants is like 1,000 times more efficient when you wound the plant first, rather than just pour the bacteria on the plant and leave it to natural openings? 1,000 times more efficient. And so this blade here, mower blade or what have you, the bed knife, the bacteria on there will be spread, as the mower continues after it has picked up some of the bacteria. And I guess what I'm trying to show in this slide here is, like, if the mower were going this way, you can imagine the spread of bacteria going from the top of this slide to the bottom. Okay, now let's move on here. I wanted to show in this slide that I think that this is fairly rare. The Acidovorax is rare. Okay, we get, let's say, 100 samples into our diagnostic lab each year. Right? Out of that 100 samples, we pull out some that are suspicious in terms of bacteria, and we run them through a biolog system, which sorts out the different bacterial pathogen populations based on carbohydrate utilization. And of all of those that were run last year, we only had 3 confirmed Acidovorax. Here's one on July 19th, and here a couple during the run on a month later. Okay, lots of times you get unidentified bacteria or non-pathogens or things like that. Okay, even though bacterial issues are suspected. There are a lot of things that can cause bacteria to accumulate in plants, and one of them actually is just the natural senescence. So if we look at some of the older leaves on a plant and we cut those leaves, we can find some bacteria associated with those leaves. Not necessarily Acidovorax, and in most cases, it's not Acidovorax, but bacteria can be there. Another thing that I would say from my observations is that suspicious samples often exhibit signs and symptoms of other disease problems. We walk into a situation with something like this, with thin yellowing turf, maybe a nondescript pattern. We can look at roots. Maybe we're going to see something like oospores or some other infection structures in roots. See this organized structure here, infection structures here. And of course, almost every time we look at roots, we see some sort of ectotrophic hyphae. So other problems are out there as well as the bacteria. Predisposing factors, we have heat and drought. We have aggressive grooming. We already mentioned something about the newer bents requiring a little bit more aggressive grooming, the top dressing, the dragging, verticutting, especially during more stressful periods of the summer. Mowing, okay, especially low mowing where you also are adding stress to those plants. High traffic areas, perhaps PGRs, nitrogen stress, maybe nitrogen deficiency, root diseases like I just showed, or other things. Here are predisposing factors that all add stress to the plants. Last year we had in 2011 we had in the Midwest some extreme heat. We had ample moisture but extreme heat. The year before that, 2010, we had moisture early, but then we had very droughty conditions throughout the summer. There are other possibilities going on here. For example, what if some of our normal practices, other than ones we just described, are changing the balance or changing the nature of that population that's in the root zone to maybe favor one species of bacterium or another? And some of this work has been, or some of these questions have been asked and investigated, actually here at Purdue, maybe 10 years ago. And the first one is frequent application of chlorothalonil. Now we're talking about creeping bentgrass greens. We use chlorothalonil quite a bit on creeping bentgrass greens, and therefore maybe the chlorothalonil is changing things to favor a blow-up of this acidovorax or any other pathogen. But through their research in looking at changes in populations, microbial populations, after frequent application of chlorothalonil, they found that there are a few bacterial populations were enhanced, but none even remotely related to acidovorax, and a few fungal populations were suppressed. And I guess that would be normal because we're applying a fungicide. So it doesn't seem, based on this, that chlorothalonil, one of the fungicides that we regularly apply to our greens, is really having an effect or influencing the nature of this particular disease. How about the frequent application of Pseudomonas aureofaciens TX1? Now, some of you might remember this little contraption here, maybe from 20 years ago, this BioJect system, maybe 15 years ago. This deal would be hooked up to the irrigation system. Bacteria would be grown in this system, beneficial bacteria, this TX1 of Pseudomonas, and injected into the irrigation, and at night the bacteria would be applied all over the golf course, and the idea there was that this bacteria would interfere with any of the infection processes of Sclerotinia, the dollar spot pathogen, and or Rhizoctonia, the brown patch pathogen. Of course, we don't see these around much anymore, and that's because they pretty much failed to do exactly what it was hyped to do. However, in this particular study where they looked at frequent application of this Pseudomonas and looking at its effect on microbial populations, they found that the thatch and soil microbial populations were unaffected. Okay, it kind of answers a couple of the questions about whether or not some of our other cultural practices are setting the stage for this blow-up of acidovorax. Possible chemical treatments. Okay. I'll go through these to some small extent, kind of run through them. Most of you are familiar with these sorts of things, but let's go through them quickly. Conventional fungicides, whether it be chlorothalonil or the strobilurin fungicides or the DMIs, they won't work. They're not going to suppress the activity of this bacteria. None of them will. So if someone tells you that they do, you're not getting accurate information. Phosphonates. Now this is phosphatyl aluminum and Shipko signature and some of the potassium phosphites. that we regularly apply. The idea here is pretty good. The strategy is good. The idea is that although some of these phosphonates actually influence the growth of maybe the anthracnose and pythium fungi, the other thing is that they're reported to stimulate some of the plant's own defense mechanisms, sort of a plant health thing, and therefore enable the plant to fight off some of this infection, okay, especially by a weaker pathogen. Again, we'll see a little bit of data here that, but nothing really, I would say, in any of these that really you can draw firm conclusions on in terms of being the magic bullet, because there is no magic or silver bullet. Hydrogen dioxide, which is xylitol, it's a general surface disinfestant, and we haven't observed any effect of this on fungal diseases, and I doubt it would do anything about the bacterial disease as well. Oxytetracycline and streptomycin sulfate, I'm not going to go into those very much because they are antibiotics and they are not legal. So I don't think it is even worth the risk, even in an experimental mode, to go into this. There's something else going on here, and there's no magic bullet, so I don't even think we ought to be bothered looking at these particular compounds. Copper hydroxide, coppers are commonly used in the plant growing and vegetable industry to slow down the spread of bacterial diseases, and the bacterial diseases in veg crops and in ornamental plants can be really serious. Really wipe things out, and copper hydroxide in combination with mancozeb, and that's what I have here, this junction product is actually copper hydroxide plus mancozeb. Some of that is used quite extensively. The downside there, two downsides. One is that, if the disease is already rolling along at a pretty good clip, you're not going to affect the rate of spread or the extent of damage. And the other thing, it's quite phytotoxic and can lead to some serious yellowing of the individual leaves. And on a putting green, if you're using this, let's say, in a protective mode, I don't think you're going to be happy with the result. Bacillus subtilis, QST713, which is Rhapsody. Again, this is a biocontrol application. The idea is that the bacteria preparation will increase on plant surfaces and outcompete or utilize maybe fungi or other bacteria as a source of nutrients because of the action of this particular bacterium on other organisms it comes into contact with. It's a theory. There's absolutely no evidence to suggest that it works in any way. The last two, I think you've been hearing quite a bit about. Of course, the mineral oil is Civitas. Again, this is induced. The strategy here is induced systemic resistance, where again the plant's own defense mechanisms are stimulated. And the idea that it can protect itself, where it can fortify itself against especially weak pathogens. We haven't found much effect on fungal diseases, but I think it's a pretty good, it's a reasonable expectation on bacterial diseases. Again, absolutely no evidence one way or the other, but it's a sound theory. And the same goes for this new component in daconil action, which is acebenzolar, a compound that's been around for quite some time, and I remember in the vegetable industry, it's also been used to try to quell some serious bacterial outbreaks. I can tell you that when the outbreak is already severe, none of these compounds are going to do much at all because aggressive bacterial pathogens will just take its toll. Again, the acebenzolar is something that stimulates a plant's own defense mechanisms, and there's again, with this as with others, there's no evidence that this is going to prevent or reduce damage in the field. And with all of these, I know that there's research going on right now, and we're going to have answers to all of these questions probably in a few months. Okay, let me move along here. I just want to point you to some research at North Carolina State University that was completed and posted on Dr. Lane Treadway's website last year. In this particular case, and just go to the NC State University Turf Pathology website, you can find these slides. In this particular case, he looked at some antibiotics against an untreated, okay, and looked at symptom severity. And then in this next one, he looked at a number of different compounds. These antibiotics, look at the rates, 10 pounds per acre. He did notice some serious phytotoxicity with this. Some dacinal action, some of these other compounds. He did find some effect with the Chipko signature right here, okay? But this is, again, this is in response to an outbreak, and this is 1 year's data. So, again, I'd be patient, and let's wait to see what else comes out in 2012. But I would encourage you to visit this website because it actually has some data posted up. Okay, here's my recommendation for you if you try any of these compounds, okay? I want you to spend an extra $20 or $30 and buy a big plywood board and put that down before you spray over that so you have a check plot on your own green, okay, right there in some of the area that's showing the damage. And mark the corners with some paint, and you will see, you will learn more from that than you will learn from reading a lot of other things, because you're going to see the result of those treatments on your own putting green. And then you can determine whether or not you spent your money wisely and plan accordingly for next year. You know, and to tell you the truth, I would do this regardless of whether you have this bacterial disease or if you're going after some of the root diseases or some of the more funkier diseases of turf. So I would say that this is an important research tool. I would encourage you to do this. I know it's a pain. Do it, though. You'll learn a lot. Okay, just a couple of observations. I got 2 more slides here, and I'm going to wrap it up. One, all of the reports in Indiana involve creeping bentgrass putting greens. They all occurred during or after stressful periods in 2010, 2011. Almost all came from high-profile clubs where we had aggressive grooming. And no chemical treatments have been shown to prevent or limit damage or hasten recovery in the field. None. Okay? We're going to find out something about this next year, by October, but at this point, that's the case. Outlook for 2012. Job 1 is to promote healthy roots with good agronomy, aerification, and top dressing in the spring. That's a month ago. Hopefully you did all that, because healthy plants are going to be able to resist this bacterium on their own, okay, much better than plants that are weakened. And of course, you know that aerification and top dressing in the spring promote excellent root growth and encourage the health and vigor of the turf. Remedial treatments, such as those that we discussed previously, will also work better, much better, on a healthy plant, which is able to kind of help itself rather than plants that are weak. Now, the working assumption is that if Acidovorax is identified in 2010, 2011, then greens are at a higher risk due to higher populations. So if that's the case, if you had a positive identification of Acidovorax in the past, I would recommend no verticutting during stressful periods. You're going to wound the plants, and you're going to further stress the plants and promote more infection. Light top dress only, no dragging. I would syringe ahead of the stress to keep the plants from going into wilt stress. Raise the height of cut. Try to include rolling or not mowing on some days during these stressful periods. Do whatever you possibly can to relieve the stress. And then if I had a 5th one there, communicate with your greens committee or your administrators and tell them what you're doing ahead of time to prevent the turf from going into stress and why this is necessary to raise the height through July and August. I think they will, if you explain the level of threat to them, I think they will be very receptive to your solutions, your informed solutions to these problems. Now, my time for my formal presentation is up. So I'm going to leave you with these thoughts. It's my opinion that this particular disease is not in itself an aggressive pathogen, caused by an aggressive pathogen, but there are predisposing factors, largely due to stress, that is causing this acidovorax to these acidovorax populations to explode in the turf and then further damage the plants. So with that, I wish you all the luck in the world in the summer ahead, and hopefully I'll talk to you again in the fall sometime. Thank you very much. I appreciate the opportunity. Thank you.
Well, thank you, Dr. Lattin. That certainly was interesting, and we greatly appreciate you sharing your insights with us today. So for everyone on the phone, again, as promised, on the screen is the 9-digit code for the CEU credit. So the number here is 999-9163-14823. And again, just as a reminder, to receive your credits, we just ask that you go ahead on the website there and make sure that you insert that number within 30 days of the webinar. So thank you again so much for attending.